All right, in this video I'm going to do a little tiny bit of section 7.4 and then quite a bit of section 7.5, which is all about solving homogeneous, constant coefficient, linear systems of differential equations with real eigenvalues. Okay, so here is what a homogeneous, constant coefficient, linear system looks like, or an example of one. So let's say we've got a dx dt and a dy dt. And dx dt, let's say that I'll put some numbers in here, 3x plus 4y, and dy dt is 5x minus 7y. Now this should look sort of familiar. We had ones that looked like this when we did like the double tank example. So this right here is called the component form. So it's the component form of the system. Okay, so this is a system because it has two differential equations. It's linear because the x and the y and the derivatives of x and y are all raised to a first power. It's constant coefficient because 3, 4, 5, and negative 7 are all constants. They don't have any t's in there. And it's homogeneous because there are no other functions of t along with those functions with x and y in the equation. Okay, so these are the ones we're going to concentrate on for the next little bit in this class. And what we need is actually a matrix that goes along with this. So I'm going to change this into kind of a vector form. So I could say that this would be the same thing as dx dt dy dt equal to, and then that 3x plus 4y, 5x minus 7y. I could say that that is x prime y prime. Let's take out the independent variable. And then on the right hand side, I could use matrix multiplication and say that that right hand side is the matrix 3, 4, 5, negative 7 multiplied by the vector xy. So now let's double check this. We'd multiply the first row by that column. So we'd get 3x plus 4y, 4y. And then on the bottom row in that vector, 5x minus 7y. I'm not sure why I made that parenthesis so small there. It should go around the whole thing. That whole thing is now a vector. Now, the generic form of this, what the book does, so the book uses bold. So it uses bold letters to denote a vector. And I think books usually do this, and I think it's because in typesetting it's easier to write a bold than it is a little arrow up above it. So what the book does, and the book uses X, which I'm not a fan of, but that's okay. So I'll do this kind of how the book does it. I'm just not a fan of it because there's so many other X's floating around. And so it's confusing what x is, because sometimes x is the independent variable. Here it's not, it's t. Instead, here it's a dependent variable, but then they're going to use it to denote a vector. So the way the book writes this is that it's got that x bolded because it's the vector. So they're talking about this vector here that's the derivative of this vector with an x and a y in it. Personally, I like to use something like capitals with an arrow up above them, just to do something different. It's not an X, it's not a Y, it's at least a capital Y prime to denote that it's a vector, and then A times some Y. Something like that is what I usually like to do. I like to use arrows instead of bold. All right, okay, so now we've got the component form, and then this here would be the matrix form. Matrix form because it's got a matrix. And that's really the form that we need these in order to solve these, because it's the matrix that's going to give us the eigenvalues that are going to tell us the solution. Alright, so here are why eigenvalues tell us a solution. So let's look at something where we've got, I'm using the book notation here of bold, so we've got some derivative is equal to a matrix times some other vector. Now, if you ask yourself, what function is its own derivative, then the answer to that is an exponential. And so let's make a guess. This isn't really, right? But so I'm going to put it in quotes. This is a very educated guess that the answer to this x is some exponential. Now, we don't know what it's to, so I'm going to put lambda in there. And of course, that's not that's definitely on purpose, that lambda. Now, this x on the left-hand side for our guess, that's a vector, but on the right-hand side, I don't yet have a vector. So let's make it be a vector. I'll make it be v. All right, now I'm tired of putting things bold, so I gotta switch it. It's bugging me. All right, x equals v e to the lambda t. So now let me take the derivative of this. So if I take the derivative so that I can plug it into this equation on the upper left of the screen here, v is a vector, it's constants, so that stays as a constant. And then if I take the derivative of e, I get e again, but then chain rule says that I'm going to multiply by lambda because that is the constant out in front of t. All right, let me plug this all into that differential equation in the upper left. So the derivative is v lambda e to the lambda t equal to a times that guess, which was v e to the lambda t. Now I've got an e to the lambda t on both sides, so I can cancel that. So then I've got, and I'm going to switch sides here so this looks familiar, a v equals lambda v. And hopefully this looks really familiar to you. This is the definition of an eigenvalue and vector. Eigenvalues and eigenvectors. So pretty cool. Really what this tells us is that if we can find the eigenvalues and the eigenvectors, then we can take a vector, multiply it by e to an eigenvalue, and that's going to give us a solution to our differential equation. Now, if we have, say, a 2 by 2 system, so two equations, two dependent variables, then what we have is two eigenvalues. And so let's call them lambda 1, and lambda 1 is going to have some corresponding vector, and lambda 2 is going to have some corresponding eigenvector as well. And so if we have the system, then our solution, our full solution, this works exactly like it has before. It's called principle of superposition. You've seen this before. If you have more than one solution, you stick constants out in front and add them together. So our solution, our full solution, is going to look like a C1 eigenvector 1 times e to the lambda 1 plus C2 v2 e to the lambda 2 times t. So essentially this was section 7.4. It basically is, it kind of has principle of superposition in there. It says if you have more than one solution, you stick constants out in front and add them together. So a 3 by 3 system, you're going to have 3 solutions, and you would have another C3 v3 e to the lambda 3 out in front of that. Right, now this is only for real eigenvalues here. So I should actually specify that. Let me say that this is 2 real eigenvalues. When you have complex ones or repeated ones, that's different, and there will be other videos on those. All right, so let me give you some steps. So here's the steps to solve constant. Do you know what? I'm going to make this easier instead of writing all that out again. Steps to solve x prime equals some matrix times x with real eigenvalues. So the first thing that you want to do is make sure that you have the right form because you need that matrix. So you want to write the differential equations, there'll be multiple, in the form x prime equals a times x. So really this is saying just find that matrix that goes with it. Then the second thing that you want to do is find the eigenvalues, the lambdas, and the eigenvectors, the v's, to A. I don't like the way that's stated, sorry. Of A, how about? That's better. So find the eigenvalues and eigenvectors of that matrix A. Then third, your general solution. We just had this on the previous slide. So your general solution, that's not a derivative because it's the solution, whoops, is going to be C1 V1 e to the lambda 1 times t plus C2 V2 e to the lambda 2 times t. And then if you are given initial conditions, apply them. Apply initial conditions to find C1 and C2. And by the way, this is for a 2x2 only. And it's really only specifically for 2x2 just because I have two different solutions, but this can be applied if it's a 3x3 or 4x4 or any other bigger matrix. And then a lot of times I'm going to ask you to rewrite the solution as one vector. So rewrite the solution as one vector. Really, I do this for my own sanity because there are infinitely many eigenvectors, and therefore there are infinitely many corresponding constants that go with them, and tracking that can be very difficult. But if we rewrite it as one vector, we'll all get, no matter what we got for V1, V2, C1, C2, we should all get the exact same answer at the end. All right, let's do it. How about with a pen? Okay. So let's solve x prime equal to -1, 4, -2, 5, where x of 0 is equal to 1, -2. Alright, so the first thing it said is to put it into the correct matrix form. We're done. We've got the matrix. Now we need to find the eigenvalues and vectors for that matrix. So we need to find the determinant of A minus lambda I. So I'm subtracting lambda from the diagonal. Now I'm going to multiply, and I'm going to multiply -1 minus x and 5 minus x. I'm going to combine those right now. So I've got a lambda squared, then I've got a negative lambda times -1, so that's +1, and a negative lambda times -5, that's -5. So I think I've got, if I combine those, I've got -4 lambda there. And then I've got -5. -1 times 5 is -5. And then plus, because this is a minus, -5 plus 8. So if I combine those constants, I've got +3. Factor. What's that going to be? -3 and -1. Set it equal to 0. And so one of the eigenvalues is +3, and one of them is +1. Alright, so for the one that is +3, I'm going to plug that back into, I'm finding the vectors now, plugging that back into A minus lambda I. So then I've got -1 minus 3, so that's a -4, 4, -2, 5 minus 3 is 2. Multiply that by a vector, set it equal to 0. and then write out the equations. Negative 4x minus 4y equals 0. From the bottom row, negative 2x plus 2y equals 0. That should be a plus, right? Negative 4x plus 4y, yeah. And I only noticed that because I couldn't choose the same x and y for both equations there. All right, so let's call this one lambda 1. So that means my v1 looks like 1, 1 will work. And then if lambda equals 1, I'm plugging it back into a minus lambda I. So I've got negative 1 minus 1, that's negative 2. 4, negative 2. 5 minus 1 is 4. Times xy, set that equal to the 0 vector. Write out the equations. 2x plus 4y equals 0. I'm not going to write the second one because it's exactly the same. So the second eigenvector, looks like if I choose 2, 1, that'll work. Because 2 times negative 2 is 4. Yep, I think that'll work. Okay, so that's my second vector. All right, so my general solution then looks like C1, V1, which is 1, 1, e to the lambda 1, which is 3, times t, plus C2 times V2, which is 2, 1, times e to the lambda 2, which was 1, times t. All right, so there's the general solution. I think that was step 3, was to write out the general solution. Now I've got to use the initial conditions, or apply those initial conditions and find the constants. So I'm going to plug in 0. So I get C1 times 1, 1. E to the 0 is 1. Plus C2 times 2, 1, and e to the 0 is 1. And that's going to equal 1, negative 2. Now, if I use all of those properties of matrices or vectors, what I can do is I can multiply in C1, multiply in C2, and then add everything together to get one vector on one side and one on the other. And really what this boils down to is looking at everything that's on the top, and I can make an equation out of that, and everything that's on the bottom, and I can make an equation out of that. So I'm going to look at the top and make an equation out of everything that's on the top of each vector. I've got a C1 times a 1. I've got a C2 times 2. And then on the other side, I've got a 1. Now I'm going to look at everything on the bottom. So from the bottom vector, I have a C1 times 1, so that's C1. I've got a C2 times 1, so that's C2. And I've got a negative 2. So now I have a system of equations here. I'd probably subtract the bottom one. Let's see what happens. C1 minus C1, that eliminates C1. 2C2 minus C2 is C2. And 1 minus a negative 2. So that's 1 plus 2 is 3. So C2 is going to be 3. And that would make, let's see, I'd probably look at this equation right here. So I'd have C1 plus 3 is equal to negative 2, so that would make C1 negative 5. All right, so now I've got, here's all my eigenvector and eigenvalue work, because I'm going to come back over here to the left. So now I've got that C1 is negative 5 times 1, 1, e to the 3t, plus C2, 2, 1, e to the t, and I'm not sure what I was thinking right there, but oh boy. I didn't, oh geez. Sorry, let me start over. Not quite. We found C1 was negative 5. Okay. Jeez. Negative technical difficulties. C1 was negative 5 times 1, 1. E to the 3t. plus C2, this is all I wanted. I wanted a 3 in there instead of C2, times 2, 1, e to the t. Okay, one more step. My very last step is that I want to write this all as one vector. So what that means, again, I'm going to look at everything on the top. So on the top, I have a negative 5 times 1. That's a negative 5, and that one is multiplied by e to the 3t. And I have a 3 times 2, so that's a 6, and that's multiplied by e to the t. On the bottom, I have a negative 5, and that one's multiplied by e to the 3t. And then I have a 3 times a 1, and so that's 3 times e to the t. Now the reason, again, that I'm having us write this all as one vector is that back up here, I don't know, let's go for this eigenvalue and this eigenvector. I could have chosen negative 1, negative 1. I could have chosen negative 5, negative 5. And the difference there would have come through in C1, but when we multiplied it all out, we still should have both gotten a negative 5 out in front there. All right, so there's how to solve systems of equations that are linear, constant coefficient, homogeneous, and have real eigenvalues.